I want to go over an example problem today. Let's kind of think back to the good old childhood days where you guys have like the Hot Wheels car and you have like the loop-the-loop. And so in order for that Hot Wheels car to go through the loop-the-loop, it is of course going to go through the loop, and at some point in time it's going to get to the top. And yeah, so when it gets to the top, it's going to have potential energy. Does it have kinetic energy? Well, if it didn't have any kinetic energy, here's what would happen. It would get to the top, and it would come to a stop, and it would fall out of the sky. And you crash in your head, and that's not good. So it clearly has to still have kinetic energy at the top. In fact, for it to be able to get around this loop, it must still have a velocity when it goes across the top. In fact, what I can do is I can probably do a little demonstration on that. All right, so in this scenario where I have a skater, when we did a skate park sort of thing earlier in the year, as long as we drop this person above, oh, there's friction, hold on, let's take away all the friction. So let's assume that there's no friction for a moment. As long as we drop them at least as high as the top of the loop-the-loop, they can go around the loop-the-loop. But that's not entirely reality now, is it? Because that does not look realistic right there. That's not how skaters work. Let's try this one more time. I'm going to change one function to it. Oh, yeah. I'm sorry, you're dead. So if we drop her from here and she's no longer attached to the track, she's going to fall off and fall on her head, and that's not good. So she clearly needs to start from higher in order to be able to go around the track and stay attached to the track the entire way. So we need to figure out how high that is, or at least how fast this person needs to be moving when they enter the track, so that way they don't fall off. You can see that right there. She just barely was falling off, and that's what we're going to try and avoid. We're going to avoid that falling off part. So let's figure out how fast someone would need to be to enter. And in fact, I want to make this fairly realistic. Let's pretend for a moment that you are actually driving a car, a realistic, real life-size car, and you're going to go around a real life-size loop-the-loop that you built in your backyard or down the street or something weird. So clearly, to make that happen, this is going to be fairly large. Let me think about how big that should be. All right, so to make this realistic, let's make this diameter about 40 feet. And heck, we might as well convert this to a metric measurement. So if I'm going to take the diameter, and that is 40 feet, I'm going to convert that into a metric measurement. So there's 3.28 feet in 1 meter. Feet will cancel, and we're left with meters, and this will give us 12.2 meters. And of course, we really care about the radius, so that means that the radius is 6.1 meters. All right, with that in mind, we know that this car, so here's the ghost image of the car, it's going to go up the track, it's going to get to the top, and it must be moving at such a speed along the tangent, so it must be moving in this direction along the tangent with some velocity, fast enough to where the acceleration, let's try that again, the acceleration towards the center of the circle must be at least enough due to the track, so that way gravity isn't the only thing acting on it. Or I suppose at minimum, gravity will be the only thing acting on it. So at minimum, this acceleration is going to be a value of 9.8 meters per second squared at minimum, because at that point in time, gravity would be acting on it. If it was moving any faster, it would have an acceleration greater than that, because not only is gravity acting on it, but so is the track itself. So the acceleration towards the center of the circle is the same thing as the acceleration of gravity, which is 9.8 meters per second squared, and this is also equal to v squared over r, where v is the velocity along the tangent that we want to figure out. We have the radius, 6.1 meters. We have the acceleration. Let's solve for v. So the acceleration towards the center times r is equal to v squared. and take the square root of each side. So the velocity at the top, and that's key, that's the velocity at the top, is equal to the square root of AR. So that's going to give us a value of the velocity along the tangent at the top is equal to 7.73 meters per second, because we have 9.8, right? This is 9.8 times 6.1, and that's, take the square root of it, that's going to give us the velocity at the top. So the velocity at the top, 7.73 meters per second. However, let's assume that someone actually is driving this car. This is a realistic thing. You know, Jacob decides he's going to drive his car, whatever jalopy he's driving, he's going to drive it in, and what he wants to know is how fast does he have to enter this thing at this location here. We know that he must be moving at 7.73 meters per second at the top, but what he wants to know is what is his velocity when he enters this thing, because you should recognize that he's going to slow down because of gravity. Well, that is actually just an energy problem. We have a height change of 40 feet, right? So let's say it's a perfectly circular track. So that means that the potential energy at the bottom plus the kinetic energy at the bottom is equal to the potential energy at the top plus the kinetic energy at the top. At the bottom, it has virtually no potential energy. At the top, does it have kinetic energy? Yes. It has, in fact, specifically a velocity of 7.73 meters per second. So don't forget that it does, in fact, have kinetic energy. You just need to solve for the velocity associated with that kinetic energy at the bottom. So let's solve for that. We have 1/2 mv squared, where that's the velocity at the bottom. The entry speed equals mgh plus 1/2 mv squared. That's the velocity at the top. So this here is what we are solving for. If you notice, mass cancels out. So the mass of the car and the mass of Jacob just does not matter, and we're going to solve for that velocity. I'm going to multiply each side of the equation by 2, so that's going to get rid of the 1/2, and that's going to multiply this part by 2 as well. So that means that the velocity at the bottom squared equals 2gh plus velocity at the, I don't know why I put the n there, cancel it, velocity at the top squared. Okay, and now I just simply take the square root of each side. Let me extend this a little bit. So the velocity at the bottom is equal to the square root 2gh plus the velocity at the top squared. Let's go through and run those numbers. In fact, let me just write them out real quick. So the velocity at the bottom is equal to the square root of 2 times 9.8 times the vertical height. That's the 40 feet, but it's not feet, that's 12.2 meters. That's the vertical height change. So 12.2 meters plus the velocity at the top, which is 7.73 meters per second, and we are squaring that. And that gives us a number. All right, so that gives us an answer of about 17.3 meters per second. So that's the speed at the bottom. Let me scroll back up. Okay, here we go. We're scrolling back up. So the velocity at the bottom is equal to 17.3 meters per second. So that's the entry speed at this location here, where we're going to drive, slow down because of gravity. Oops. And by the time you get up here, you're moving 7.73 meters per second. You are staying just barely connected to the track. You're essentially at that point where the wheels are about to separate, and it allows you to stay connected the entire time. You don't lose control, and Jacob survives and goes. The problem is that two things. If he's actually realistically doing this, there's a couple things we want to know. For one, he wants to know how fast this is in miles per hour, because that's what his car reads. So if we have the 17.3 meters per second, let's convert that to miles per hour. So we have, let's see, 1,609 meters in 1 mile, and there is 3,600 100 seconds in 1 hour. So seconds cancel, meters cancel, and we're left with miles and hours. That will give us 38.7 miles per hour. Okay, so that's 38.7 miles per hour. Those are the same thing. Oops, did not mean to do that. I should just not have done any of that. Try that again. 38.7 miles per hour, and that's what he's going to actually read on his speedo, which reads our silly American units. The other issue too is, if he realistically wants to do this, now he knows how fast he's going to be going entering this thing. He probably wants to hit the gas pedal only just enough to overcome friction, right? Because he could either put it in neutral and assume that there's no friction in the system, or maybe he could just keep the gas on just enough so that we can overcome that friction. And that's fine. The other thing is too, is he going to black out from the g-forces, right? So where is he going to experience the greatest amount of g-force? So this is going to be at the bottom, because your velocity is the greatest at the bottom, and of course, as we expressed earlier, right, the acceleration is equal to v squared over r, so if your velocity is greatest at the bottom, then your acceleration is greatest at the bottom. So let's solve for what the acceleration is that Jacob would be undergoing at the bottom. That's pretty simple. So the acceleration is equal to v squared over r. We know the velocity at the bottom. Of course, we're going to use the meters per second for that. So that's 17.3 meters per second, but that's squared. And we're putting that over r, which is a radius of 6.1 meters. So that's going to give us a value of 49 meters per second squared, or about 50, right? I'm going to go ahead and round that off to 50 meters per second squared. Considering that gravity is about 10 meters per second squared, that's about 5 times greater than just standing here. So we are looking at about 5 G's of acceleration due to the track. And I'm going to say that again to be very clear about that. That's 5 G's of acceleration due to the track. So how many G's of acceleration does he really experience? He's actually going to experience 6 G's, because we have to add in the 1 G that he's already experiencing just by simply standing there on the track, or by sitting in the car seat. So in total, he's going to experience 6 G's entering the track. Is that enough for him to pass out? Squeeze your butt a little bit. Probably not. Get that blood flow into your brain. Here's the example problem that I wanted to go over, and I'm actually hoping that I can link something here. All right, so actually I'll pause it for a second. So my numbers were not just theoretical. It actually comes off of this video. So there's some guys that did this in real life, and here in the video, I'm just going to kind of show you the first 30 seconds of it, and then you can track the video down, or I'll link it so you guys can find the video itself.
It's talking about his next life because it's the biggest and fastest thing this year has ever done. Wheels are really got off someone down. There we go. Yes. So what we wanted to know is, could we do that in a real life family size car?
All right, the bell means that's my time. So I'm just going to link this video into the description, and go ahead and watch it, and you'll see that their numbers that they come up with are the same as ours, at least for the most part. If you pay close attention to them, you'll see that they kind of fudge the numbers a little bit. But yeah, so it kind of shows that the math behind it actually isn't that hard, even though they might make it seem like it is. Have a good one.